Elaborate.
Like a hydrogen, I guess, is attached to nitrogen since it has lone pairs, and then like the oxygen puts the electrons to clear out, that way the nitrogen leaves as a neutral.
Okay, so we don't like nitrogen leaving charged, right? So we want to protonate it first. To protonate it, what do you need? You need a hydrogen. So what do you need? What things would supply hydrogen?
Acid.
Cool, I needed acid. What happened in step 1? I added a base. So if you're now adding an acid, what happens to your base? Your base disappears. And if your base disappears, does step 1 happen? No. Okay. If you want to sit, you can sit again. So I like your theory. Unfortunately, it's not going to hold a lot of water. Okay, so one of the things that we noted within our energy diagrams initially is we liked to have the idea of the product being lower in energy, but we established that the product is not lower in energy because if we look at the leaving group, in this case, it would be a negative nitrogen, and that negative nitrogen is higher in energy than our negative oxygens all the way through, which would suggest your product, as it states or as it is currently set up, is higher in energy than our reactant, and therefore, should this reaction occur? No, it'd say it doesn't. Okay? So again, this is where question B comes into play. Does this mechanism accurately describe the conversion of an amide to a carboxylic acid? So if we look at our starting functional group, our reactant is indeed an amide. Okay? For kind of reference, in case we need a little reminder on that, that's a carbonyl directly bonded to that nitrogen. That's an amide. Okay? Technically, when we refer to the amide, we're referring to that bond, I believe, if we wanted to get uber specific. And then we've got the carboxylic acid as a product. Okay. We're real new in this content, so maybe you haven't gotten to this part of the lecture content, and so you're unfamiliar with this kind of overall process. That's okay. So we can still kind of reason our way through it. If we wouldn't expect the amide to convert to the carboxylic acid, maybe the intent of this question is saying this is a BS reaction, it's not going to happen. Right? Seems like a reasonable conclusion. Okay, but if we follow along with the wording behind this, does it suggest that it's a BS reaction? I want to convert the amide to a carboxylic acid. Does that phrasing suggest that you can indeed convert an amide to a carboxylic acid? It's kind of hard. I mean, trying to read between the lines on that. Okay, and yeah, it actually turns out, yes, you can absolutely convert an amide to a carboxylic acid. In fact, we leverage this heavily within this chapter to make primary amines. If we talk back or go backwards, all the way back to Unit 1 of this semester, we talked about nitrogens as nucleophiles. Okay, remember if we had the bromine and we tried to react that with NH3 to then do the substitution reaction where we had the NH2. We said that that reaction was ultimately trash because one of the products that comes out of that is a nitrogen with a lone pair of electrons. And what is that lone pair of electrons good at? Acting as a nucleophile, so it can attack again. And so what ends up happening if we use nitrogen as a nucleophile is that we get a mix of products. You would get all 4 of these products. So if I just wanted to make a primary amine, I don't have a good way of doing it because if I try and use the nitrogen with the alkyl halide, I get this giant nasty mixture of products, and that's ugly and messy and very challenging to kind of separate. So when we talked about nitrogen as a nucleophile, we said ultimately it's bad at doing substitution reactions. It's not bad, it's just overly good at doing substitution reactions, so we can't control it. Okay, which meant that we didn't use it to do substitution necessarily. We used it and we exploited that to push us all the way up to a system like that, the tertiary amine. Because once we are at the tertiary amine, we now have a great leaving group and we have the potential to do an elimination reaction. That was the Hofmann elimination. So when we think back to that very first unit, that's what we did with our amines. Okay? We weren't able to get primary amines. Okay? This conversion of an amide to a carboxylic acid is actually something that we can use to leverage to make amines. Okay? It sounds a little bit strange and out there, but that's why it's a named reaction. Okay? And it gets referred to as the Gabriel synthesis. Okay? So we don't have to stress necessarily about that, except that this reaction does indeed work. Okay? The amide to the carboxylic acid absolutely does work. But if we look at the energetics behind it, would we expect this to work? No, not at all. Okay? So that means we must be missing something. What are we missing? Nope. What product did we make? We made an acid and a base. And what do acids and bases do when near each other? They react. This can immediately remove the hydrogen, dumping the electrons onto the oxygen. So our reaction continues. And we'd form a negative oxygen. And what would happen to our nitrogen? It's now neutral. We don't have that negative nitrogen anymore. We have a negative oxygen. But is a negative oxygen any better than where we were? No, it's not. It is. It is actually. It's a lot better. And we now actually drop down to a product level more appropriate to where we want. How is it that much better?
Because of the resonance.
The carboxylate has resonance. That resonance stabilization is what drives this reaction. If we go back and look at these look like universal unidirectional arrows. They aren't unidirectional. They're actually reversible arrows, and for the most part, they're very much reversible in the wrong direction that we want them to go. But that last step, we'll call it our black star, very irreversible, okay? Because we're now forming a very stable structure. Okay? That stable structure is the carboxylate. It's one of the lowest energy forms for our acid derivatives, which is what this unit is about. And we'll come back to what that term means in a second. And that's what drives our reaction forwards. Okay? The question officially says the amide to a carboxylic acid. Well, what's going to happen to get our carboxylic acid? What's that? I need a hydrogen. So, second step, I add hydrogen. Okay? So we've done that tons of times before. We have a second step and we add H+. If we consider what happens within these particular reactions, we rarely, if ever, talk about the addition of that H+ as a second step. Okay? And this is something we've mentioned in the past. The acid workup is sometimes shown as an explicit step and sometimes not. This is one of those cases where it's typically not shown as an explicit step. Okay? And because Ivan had suggested that we add the acid initially right away, okay, this is where we have to be careful. This is a second step. This is not getting added to neutralize the hydroxide at the very beginning, which shuts down the whole reaction. This is getting added after the fact. Okay? And that's what I was saying. I wanted the acid to neutralize the nitrogen. The acid isn't neutralizing the nitrogen. The acid is neutralizing the carboxylate salt. Okay? This was something that I believe even on Tuesday, our past lecture, that we had that same issue. We made a product, and then we had to carry past the product, and then we doubled back to the product. And why do we have to do that? We have to do that because that's what the chemistry dictates happens. That's the only way we progress forwards. And we can see that within our energy diagram when we look at the energy of each of those reactants and potential intermediates. And so what happened with this student's mechanism is they didn't fully process what has to happen. You have to go through and do that extra acid-base step. Kind of, sort of? So when we look at question B, does the mechanism accurately depict the conversion of an amide to a carboxylic acid? Believe it or not, I would accept both answers. You just have to be real careful with how you answer each of them. Okay? So no, it's not accurate because this doesn't show the complete mechanism to convert to the carboxylic acid. It has to go through and form the carboxylate. Once it's formed the carboxylate, then we can reform and make the acid. Okay, so they're technically missing 2 mechanistic steps that they didn't specify. You could also go through and say, well, yes, it does, because I've made the amide into the carboxylic acid. Structurally, mechanistically, yeah, sure, that's what happened. Did that happen in the real world? No. And that's why saying yes would be technically a bad answer, but you could explain a way to get probably half points because you're using the logic of what's in that system. Flawed, but you're at least using that logic system. Does that make sense? Okay. Questions about that? Okay. I want to push out a couple kind of new things. So we'll go to a whiteboard here. Okay, I made reference to a word that I said acid derivative, and we're going to come back to it. Okay, what you're going to find is this particular unit talks a lot about what's known as acid derivatives. Okay, well, what is an acid?
Proton donor.
Cool, that's awesome. We go back, our definition of acid is a proton donor. And we say, okay, well, is an acid derivative then anything that can donate protons? We aren't using acid in that sense here. Unfortunately, organic chemists are being a bit of dipsticks and using the same word but in a different context. When they're saying acid derivative, they're not talking Bronsted-Lowry acid. What are they talking? Nope. They're like Lewis, because that's the other definitions for acids and bases. Carboxylic. They're referring to the functional group, carboxylic acids. Okay? And so if we look at the functional group of a carboxylic acid, I'm going to make some modifications here. This is our functional group. We have the carbonyl, and then we have the OH connected to it. Well, did we just talk about a derivative of the carboxylic acid? We did. We actually talked about 2 of them. We have our carbonyl, and then it's bonded out to O-. That's a carboxylic acid derivative. It's technically its conjugate base. Okay? Note, where am I drawing this new derivative? Below it. Why would I draw it below it? I've got all this space to draw. Why am I drawing it below it?
Less energy.
Why is it less energy?
Resonance.
The resonance within that structure helps to stabilize the overall electrophilic carbon. Okay, so even when we're talking about acid derivatives, really what we're referencing is the reactivity of the carbonyl carbon. And so when we're drawing that carboxylate lower in energy than the carboxylic acid, what we're trying to actually call attention to is the fact that the carboxylate is less electrophilic than the carboxylic acid. Okay, and why? It has a better ability to do resonance. Okay, what other derivative did we talk about? There was another one. Yeah. There was the nitrogen. Yeah. Sorry, I had to think internally, and we'll come back to that internal thought in a second. Okay, we had the nitrogen. Okay. Where did I draw it this time? So we could go through and do our names on this. That's a good thing we could potentially add. So we have our carboxylic acid. We have our amide. And then we have our carboxylate. Okay. Usually we'll even throw in the word ion to make sure we know it's the charge thing. Okay. Where else did I draw it? Where did I draw the amide?
Between the carboxylic acid and the carboxylic.
Okay, cool. Why did I draw it there? Why is it higher in energy than the carboxylate?
That nitrogen's charged, isn't it?
That nitrogen is not charged.
Oh, no.
Okay. The nitrogen with 3 bonds and a lone pair, technically the lone pair was implied, okay? But that lone pair being implied, we have a neutral nitrogen. Why is the carboxylate lower in energy than the amide?
Carboxylate has resonance.
The carboxylate has, so the amide can't do resonance?
Well, it can.
That charge has a better opportunity to do that resonance than the nitrogen will. Okay, so that charge is the larger driver behind that resonance system. So if we're going through and evaluating it, the carboxylate's going to be more stable because it has better resonance than the amide. Cool, that explains why the amide is above the carboxylate, but I didn't draw it above the carboxylic acid. Why not? So acids, you're like, oh, well, it's an acidic one, Mike. That's why it's higher in energy. Are we talking about the acidic hydrogen? No. The electrophilic activity of the carbon. So it has nothing to do with the acidic character. So referencing the acidic character isn't useful. I care about that electrophilic carbon. So if I'm drawing the carboxylic acid higher in energy than the amide, what am I saying about the electrophilic character in the carboxylic acid? It's greater. Why?
Is it because nitrogen isn't as electronegative as oxygen?
If we consider the resonance options, they both have the same resonance options, okay? But we don't even have to, well, we do technically have to get to resonance, okay? But when we're looking at those resonance options, what we would evaluate is nitrogen has a lower electronegativity than the oxygen, so it is therefore better or more willing to share its electrons, making the amide lower in energy than the carboxylic acid. Okay? Why is this particularly relevant to us? What was the previous question asking about? How do I convert the amide to a carboxylic acid? How do I go up in energy? Do we go up in energy well? No, in fact, we don't go up in energy, we go down in energy. So the only way to go through and get the carboxylic acid formed from the amide is to actually go down to the carboxylic acid, and then from the carboxylic acid, I can push all the way back up because what can I add? I can add a strong, and I would argue here, acid in the carboxylic acid to force that reaction back up. All I'm now trying to do is put on that hydrogen. I'm allowed to be able to pull that off. I can't do that with the amide because we're talking about different characteristics. We're talking about going down in energy, we're talking about the electrophilic carbon. To go up here, we're talking about acid-base chemistry. Those are different chemistries, which is why we can navigate up or down for different reasons. Kind of, sort of? Cool. So what we've now done is drawn 3 acid derivatives. What was the difference between these derivatives?
The electrophilic of carbon.
So true. Why was the carbon electrophilic? What was the difference between these structures that made that carbon electrophilic? Okay, that works. That might be getting to why are you scribbling vigorously in purple?
Size?
Look at the thing that's different between those 3 structures. What color is it? It's the purple one. Yeah, it's the thing that it's connected to. Okay, so what else could I connect there?
Whatever you want.
Whatever I want. If I put a hydrogen there, would that make sense to call that an acid derivative?
This is an aldehyde.
No, now it's an aldehyde. We wouldn't call it well, why not call it an acid derivative? And yes, we could say, well, because I call it an aldehyde. I call an amide an amide. Just because I call it something else, what doesn't suggest that? What makes the difference between the aldehyde, purple hydrogen, versus all the other ones? What's that?
Can't speak for you.
It's a leaving group ability. In the case of our acid derivatives, we're talking about OH, nitrogen, and oxygen. All three of those atoms, oxygen, nitrogen, and oxygen, all have the pseudo capability to act as leaving groups. They're electron withdrawing from that system-ish. Okay? Whereas if we look at the carbon-hydrogen bond, that's a non-polar covalent bond. In the other cases, they're all polar. So it doesn't fit the pattern for our acid derivatives. Okay? Which is why we don't talk about aldehydes in this section of acid derivatives. We talk about it first. We talked about it in our last unit, where we could then be like, that's an electrophilic carbon because of the carbonyl and all that. And now what we do is say, well, what if it wasn't hydrogen? What if it was an electronegative atom? Well, now that's a polar bond. How does that change the chemistry? That's now my acid derivatives. So now I got to worry about carboxylic acids, amides, and carboxylates. Well, what else could be that electronegative atom? What's that? Yeah. So I'm not quite sure. Saying soften your answer, I don't think necessarily is going to change it. But if I say soften your answer,
Well, it's supposed to be bromine.
bromine is softer, yes. But now we can go harder. Chlorine. Chlorine, bromine, and iodine, typically chlorine and bromine are the more relevant ones. Okay? And we typically don't look at fluoride or the iodide. Both of those largely are just difficulty with that chemistry. Okay? So really we could classify it as X, where we're talking about any of the halogens. And usually when we're talking about those X's, we're talking about chlorine or bromine. Could be iodide. I don't think you'll ever see fluoride. Okay? And the issue with fluoride is it's so small, it actually creates really strong bonds. This is one of the reasons why it's very explosive, and we tend to avoid using it. Okay? Elemental fluorine and organic molecules is not a pretty picture. Okay? Which goes all the way back to our radical stuff back in Unit 4 of OChem 1, okay, at least in my class. When we talk about doing the radical brominations, we do radical brominations. We didn't do radical chlorinations. Why not? Chlorine was not selective. Radical bromination, we did a substitution for a hydrogen at the most substituted position. We replaced it with a bromine. If we tried it with chlorine, what happens? Any hydrogen reacts. Okay? That any hydrogen is then now going to be dictated both based off of reactivity of our chlorine and the number of hydrogens at that individual substitution pattern. And it becomes this big convoluted thing that involves calculations that I don't want to deal with. Okay? We didn't do iodine. Why not? Iodine is even better than bromine. It's very selective. Okay? But if we think about selectivity, what's a necessary repercussion usually that comes with selectivity? If you don't care who you date, how often are you single? You're not single. Okay? If you're very selective about who you date, you're very single. Okay? Iodide is very selective. So its reaction is incredibly slow. Okay? Slow enough to the point we don't want to wait for it to actually occur. It gives us awesome results, but those results take ages to go through and produce. And we talk about ages, we're usually talking about days, maybe weeks to actually get a yield. Bromine, you're running maybe a couple minutes, maybe an hour, and you're fine. Chlorine, we're talking about seconds. Okay? What happens with fluorine? Goes even faster. So fast that it's actually explosive. Okay? So we avoid that. Okay? Generally speaking. Unless you want to make Teflon, and then you do that. Okay? But controlled environment, theoretically, makes that safer. Okay? So, I don't know what we're talking about. Our X. Okay? So typically when we're talking about that X, we're really only talking about chlorine and bromine. Okay? Why would I put those even higher than our carboxylic acid?
Because they're acidic.
Acidic? Where's the hydrogen? Don't owe me. Where's the hydrogen?
At the X or
There's not a hydrogen, okay? If there's no hydrogen, we're not talking about acids. So why would I draw it above?
Is it because you have two electrophilic constant? Or no, excuse me.
Still only one.
Because halogens are really pretty good leaving groups.
So we could try and reference the leaving group ability, and it gets a little bit questionable there based off of our energetics for these. If we're looking at the ability for these things to go through and react, our energy diagram is relatively exothermic. Okay, why does that become a big deal? Okay, if it's exothermic, you're talking about the leaving group down here. The speed of the reaction is dictated up here. Okay, so referencing the leaving group ability becomes a little bit questionable. Does it work? Yes. Okay, but can we do better? What are we evaluating as far as the reactivity goes? The electrophilic carbon, that blue dot. All of these cases, they have the carbonyl. What we're asking about is the atom next door. Okay. Are our halogens as good as doing resonance as the oxygen? No. They're even worse at doing the resonance. And if they're worse at doing the resonance, what does that do to the electrophilic carbon? Makes it more electrophilic. That's why it's higher up in energy. Okay? So you can evaluate that differential by just evaluating the ability of our charge size electrostatic resonance on our starting material, evaluating that electrophilic carbon. Looking at leaving group ability is a questionable method. It works. It's technically wrong. Okay? So what is this new functional group called? You'll typically hear them referenced as acid halides. I'd initially written up there acetyl halides, but I think acid halides are typically what they're referring to. Again, it's not acid as in proton donor. It's acid as in this was a carboxylic acid where I changed the OH to a halogen. Okay? So that's where that name is coming from. And what we've now got is a ranking of electrophilic characteristics. Okay? And we could now go through and run all of those nucleophile addition reactions that we did with our aldehydes and technically our ketones, okay, from our last unit, now with all of these species and say, well, what happens? Do I see any new things come into play? Are there any things I need to be concerned about? Are there differences? Okay? Are there nuances within it? Of course there are. That's why it's a whole nother 2 chapters. Okay? But what you're doing is running that same core fundamental chemistry. Your nucleophile comes and attacks the electrophilic carbon. We break open the pi bond, just like we did before, and now we say, well, there's 3 very electronegative elements connected to it. Those electrons are going to come back down, reform the carbonyl. What's it do now? Does it kick out the leaving group? Does it kick out the former group or the new group that came in? How do we decide that process? And that decision process is going ultimately back to charge size, electronegativity, resonance, induction, all that fun jazz to try and figure out what should happen. Okay? There will be cases where that charge size, electronegativity stuff doesn't work out for us, and we end up encountering weird exceptions. One of those weird exceptions we talked about on Tuesday, because today's Thursday. Anybody remember that weird exception that you should memorize? Mildly inappropriate. Talking about males, most males, not eunuchs. Mildly inappropriate. It's probably underplaying this. It's probably fully inappropriate. Diisobutyl aluminum hydride. Are you now processing why it's mildly inappropriate? Okay. If you don't get it, don't worry about it. You don't need to get it. Okay, diball is one of those weird things that does strange chemistry. That's something that we should go through and memorize. That's not going to be super clean within dealing with our charge, size, electronegativity, all of that. For the record, what did diball do? Gave up H minus to what? Okay, so yes, it gives me H minus, but so does lithium aluminum hydride, so does sodium borohydride. So knowing H minus isn't necessarily a bad thing, but that doesn't allow me to differentiate it from everything else, and I need to be able to differentiate it from everything else. Stops at the aldehyde, that's a good thing. That might be all you actually need. If you knew that, you're probably good associating diball and make an aldehyde. Okay. Officially, you also have to tag in what it comes from. It's starting with esters. Which fun story brings in another issue. What does an ester look like?
It's the carbonyl with the oxygen with more carbons on it.
With more carbons on it. Did we draw up the ester functional group yet? Because that's an acid derivative. So that would be a good guess. Should that be drawn up here? Because there's a suspicious white space there, right? Is that what you're saying? You're like, there's got to be something. Mike's being super clever there. That was sarcasm for the record. Mike's not super clever. That guy's an idiot. I don't think anybody watching these videos knows what my name is, so it's fair, unless you're in my class. So, okay, is that a good place to place it? Okay. Should it be less reactive than the halide?
Yeah.
Why?
It has access to like resonance chemistry with lone pairs.
Yeah, the lone pairs on that oxygen can absolutely do resonance, and the halide really can't. Okay, it's a bit over the top to say halides can't. Okay, but it's pretty close. So it should be lower than the halides. Where should it be relative to the carboxylic acid? Ooh, is that a stumper? I think that's a stumper. Guess where it should be? You say below it. Anybody else want to venture a guess? They're the same. Your esters and your carboxylic acids are close enough in chemistry that they're effectively the same. Okay, so there really is no difference for them. Okay, which then takes us back to your initial statement. There's this suspicious white space. What's in this suspicious white space? Well, depending on how far you've moved through the lectures, you may or may not know. You may not remember the name of it either.
Well, it's like an oxygen with two ketones going to. I don't know, I forgot what the name was.
Yeah. Are those ketones? So carbonyls is a fantastic answer because that's a straight up cop out. You're like they're carbon oxygen double bonds, dude. That's what's next to it. Don't ask me about the whole functional group. Okay, that's a lovely answer. Okay. Well, what's the functional group? You're like, it's an ester, right? But is it an ester? Because with esters, this R group can't change that chemistry. Is this R group changing that chemistry? Are they related to each other? Yeah. So it's not an ester. We didn't watch enough or remember enough. I mean, you clearly watched enough. You knew what the structure was.
Yeah, I just didn't write that down.
Cool. Which is fine. That's good. Like, structure is more relevant. Okay. The structure or the name for this is an acid, go figure, anhydride. Right? And the name, believe it or not, actually isn't all that bad if you understand a little bit about its chemistry. Okay? Yeah, though the anhydride is a little bit weird. If we talked about something that was anhydrous, what does that mean? This is now a lab question. We've worked with a couple things that were anhydrous. We worked with sodium sulfate, anhydrous. Every time we work with sodium sulfate, we start with it as anhydrous. We worked with THF as anhydrous when we did the Grignard experiment.
No hydrogen?
Unfortunately not. And yeah, it's real, because hydride, hydrides, that's H minus, that's the diball stuff. Because THF has lots of hydrogens. Well, lots, eight hydrogens. Yeah, that's exclusively as a solvent in the case of the Grignard. But we had to use THF anhydrous. We couldn't use THF hydrous. Well, what's the difference between hydrous and anhydrous? Well, if we knew what hydrous was, we'd figure out what the an just means not. So if THF was the solvent, when we ran the Grignard experiment, what was the big deal about our solvent? We couldn't have water. What are some other names for water? Hydrate, hydrous. So when we're talking about anhydrides, really what we're saying is we've taken an acid and we've removed water. That's it. Okay? So if I go back and take a look at a carboxylic acid, right? And I try and remove water, what's going to happen? I got to remove, I can remove the OH. That looks like half of water, right? But then what happens to my carbonyl? It's going to be really, really, really positive. That's going to be a problem. Okay, and I would have OH floating around, right? The OH would be negative. I can't have those charges. But if this was a carboxylic acid, so it's acid anhydride, what else is floating around in solution? More acid. Like it's an acid solution, right? And what could we do? We could have the OH pick up a hydrogen to make water, and what could the oxygen do? Connect over to our carbon to make the acid without water. Okay, that's the acid anhydride. Okay, the acid anhydride, as we clearly showed, is higher in energy than our carboxylic acid, lower in energy than our acid anhydride, or than our acid halide. Why is it lower in energy than our acid halide? Resonance, it's oxygen. Resonance, yes. Resonance can potentially stabilize it, makes it a little bit more stable than the acid halide. Okay? The carboxylic acid also had resonance, also using an oxygen. Why is it higher in energy than the carboxylic acid then? Careful. Okay? If it can do resonance in two different places, what would that say about its reactivity? Shouldn't it be lower in reactivity? Because it would be really stable. So it's not that it can do resonance in two different locations. It's that once it does resonance, what can it not do the other direction? Resonance. Okay? So it's the fact that there's two carbonyls there. Resonance is occupying one of those carbonyls, stabilizing it, but once that one is stabilized, there's nothing to stabilize the other one. That's why the other one becomes more reactive than we would expect for a carboxylic acid or an ester. So the acid anhydride is more active than our acids and esters, but lower in activity than our halides, because there is still some of that potential to do resonance. Kind of, sort of? And what do we now have? All of our acid derivatives, ranked now via energy. And as we talked about with our starting kind of question, and we're going to erase some stuff out here. I'm going to get rid of this. I don't want this. And I don't want that either. Or that. Okay. We can work our way down this system pretty well. Esters and carboxylic acids are effectively equivalent, which means they're in equilibrium. They can go backwards and forwards with each other. Okay? We can work our way down really, really well. But we struggle to do what? Go back up. Okay? So when we look at how we would interconvert between these, the amide goes to the carboxylic acid. The carboxylate ion. To get to the acid, what do I have to do? I have to go back up with H+. So I'm running a special acid-base reaction to force that reaction up. Okay? But if all I can ever do is go down the ladder or even up halfway to the carboxylic acid, I'm going to have a problem. Because then that means once I've used up all of the acid halide in the world, what happens? It's gone. And I can't do it anymore. Okay? Organic chemistry is a young field, but it ain't that young. We're somehow able to get more acid halide. How do we get more acid halide? What's that? How? I can't make it necessarily, sort of, with any of the acid derivatives because the acid derivatives are all lower in energy than it. Okay? But just like with the acid-base reaction, I have to react it with something that forces that reaction. So it's uber reactive. There's something higher in energy. Okay? How could I get a halogen onto a structure? How do we typically get halogens onto structures? Just general, blanket statement. Substitution. Do I have substitution reagents that would allow me to get halogen onto a structure? Yeah? What reagents? That's a hard question. Yeah, you could cheat. If you think you got an idea on where to look in your notes, yeah, go for it. Okay. We can convert the OH to a halogen. We have the ability to do that. That's a reagent that we actually talked about back in Unit 1 of this semester. There's technically two of them that we could use. Thionyl chloride, SOCl2, or, what's that? No. I don't think zinc chloride works. There it is. A little bit of peanut butter, or PBr3. So thionyl chloride will convert NeOH. Okay? And this was one of the things when we talked about it, I was like, you're going to need to know this. It converts NeOH into a halogen. Okay? So you're running special secondary chemistry with your thionyl chloride or your PBr3 to jump the carboxylic acid up to the acid halide. What if I start with a carboxylic acid? How do I get an acid anhydride? Because the acid anhydride is higher in energy than the carboxylic acid. How could I do it? Yeah. If I start with a carboxylic acid and I want to get an anhydride, the anhydride's higher in energy. The only way I can get to it is jump all the way up to the acid halide. Once I'm at the acid halide, I can drop down to the anhydride. That's how that system's going to work. Okay? So we will almost always start with things lower on the totem pole, and we have to figure out how to get higher. Okay? That will be one of the kind of more complex questions that you'll see. Okay? Because we're concerned about how we could interconvert between them. Right? The less complex questions, if you want to call them less complex, is taking all of those reagents that you learned back in Unit 2, okay, the hydrides, the carbides, your Grignards, okay, all of those reagents, how do those react with each of these electrophiles? Okay? Because those reagents had varying nucleophilic characteristics, right? But we were ultimately just looking at aldehydes and ketones, and they had effectively the same electrophilic characteristics. So all we really cared about is how's the difference of the nucleophile character going to change how it reacts with our electrophile. Now we've got an extra problem, because I have all of those reagents now with varying nucleophilic characteristics, but I now also have varying strength electrophiles. That's going to create effectively new lines within it, okay? Where our reagents will only react with things above this level of reactivity or below this level of reactivity. Okay? So it's useful to know where they're at and try and pick out and find that chemistry. Okay? Along those lines, I'm always kind of shocked a little bit and never quite understand. I mean, I sort of understand why. We're talking about acid derivatives, so this is the ladder system that we talk about, and we use these and we talk about these, and you'll see this show up through all of the textbook and through everybody else. Okay? But what we're talking about is an electrophilic carbon, right? Well, do we know anything about electrophilic carbons? The answer is yes. Yes, you do. Yes, yeah, Mike, we totally know stuff about electrophilic carbons because we just had a test on it. And that test told me that I needed to know something about my aldehydes and my ketones. And if I looked at the aldehydes and ketones, what did I note? Where did I place the aldehydes? Why would I place the aldehydes above the ketones? They're high. Why are they higher in energy? If carbon is more I'm going to switch and say what you're saying is the blue carbon in the aldehyde is more electrophilic in the aldehyde than it is in the ketone? Is that what you're saying?
Yeah.
Cool. So you're saying the exact same thing she just said, you just use better words. That's a good level up. I like that. Okay? But why? Why is the aldehyde carbon more electrophilic?
Well, there's a hydrogen, so all the electrons are just going out to the oxygen, which is more electronegative. Like there's less things pulling on the carbs.
What is that less substitution? So ultimately our difference there is between hydrogen versus carbon. And what is carbon? How is carbon different than hydrogen?
Bigger.
Why is it bigger? What does it mean to be bigger in chemistry? It has more electrons. And because it has more electrons, what does that do to the electrophilic carbon? Stabilizes it and makes it more stable. Ta-da! We're using those things to predict those differences. That's awesome. Okay? So we talked about electrophilic carbons. We know about electrophilic carbons. We know how aldehydes and ketones react. How about we figure out where aldehydes and ketones belong in this sequence? Because if you know how aldehydes and ketones are going to react, and you put them into this sequence, you now already have a step above potentially where all your nucleophiles are going to react. So where should we insert the aldehydes and ketones? Are they more reactive than carboxylates, or are they less reactive? I asked you. You can't ask the question back. Not fair. What's the reactivity we're talking about? So if we compare the aldehydes, our ketones to our carboxylates, what's the difference? The oxygen. Well, what's the difference between the oxygen versus the carbon? True. Oxygen is more electronegative. What rule are you using to explain your difference in reactivity? by saying electronegativity, you're not saying charge. So I disagree. If you're going to say electronegativity, what rule are you using? You have a bit of a cop-out. Okay, I'll accept 3. The third rule, because it's charge, size, it's electronegativity, Mike, that's what I'm using. What's the reactivity we're evaluating? The carbon. So when we use electronegativity, we're referring to the atom where our chemistry is located. So when you're using electronegativity to explain the difference in reactivity, you're saying the carbon in the carboxylate is more positive than the carbon in the ketone because of electronegativity. Is carbon a different electronegativity than carbon? No. So you're not using electronegativity to explain that difference. You're talking about how an atom connected to it affects the chemistry. What property of that atom are you using? You can say it. Or not, I'll say it for you. Electronegativity. I'm not writing electronegativity. Sorry, I had to repeat that to myself, to remind myself. These were all atom effects. You now need to move beyond the atom effect, and you have to move to a molecule effect. And so you could start to talk about resonance begins with R, for the record. But the O that you're talking about, okay? You said the electronegativity of that atom. Is that resonance? No, what is that?
Induction.
That's induction. So you're using induction. When we go through and talk about these, what is resonance? Resonance is the ability to move electrons around through a larger space. So resonance is looking at the molecule size. Induction is looking at the molecule electronegativity. Okay? And if you're going to invoke electronegativity from this atom to explain that, you're telling me there is no resonance effect. So when I compare the carboxylate to the ketone, there is no resonance effect? Ooh, okay, dang, it has resonance. So don't tell me about the inductive effect yet. Tell me about the resonance effect. What is that resonance effect going to do to the electrophilic carbon? Stabilize it, which means? The ketone is higher than the carboxylate, or the carboxylate is lower than the ketone. Make sense? Cool. But I like that, because we're like trying to figure out where should I rank it? Where should pick a spot? Boom, done. Damn, it's higher than that. Okay, well, what next? So you could try and do that all the way. Okay, so what do you want to compare the ketone to next? Okay, the amide. Same argument. Resonance. The nitrogen has that resonance ability. The carbon does not.
Is it like below the halide?
So we could jump all the way up to the halide. Okay, is it just below the halide? Okay, because the halide doesn't really have that resonance effect, and now we're looking at electronegativity. So it should be below the halide. Yes, I absolutely accept that. Okay, which is the other flip. We're like, this is getting really obnoxious going up from the bottom, so let's turn around and go from the top. Okay, fair. What happens with the acid anhydride?
Because it can resonate?
It can resonate, but only one side, which means
Ketone's more stable than it?
the ketone is more stable than the anhydride. Which means where do our ketones and our aldehydes sit?
Between the hydride and the carboxylic acid.
That was not very graceful, but it's between the anhydride and our carboxylic acid / esters. Right? They aren't officially in the ranking within this unit because this unit is nucleophile addition followed by elimination. And to eliminate, you must have a leaving group. Right? But our aldehydes and ketones are effectively doing that same chemistry. They just can't do the elimination part. So if you can recognize where they are within this kind of pseudo ladder, that can help you start to leverage the information you already know about predicting where that chemistry falls for those individual reagents back to the derivatives. Kind of, sort of? So, question? Are there any questions? Can I delete everything? Yeah, you can take a picture. You can take a picture or go to 55 minutes and 40 seconds. Okay. 3, 2, are you taking a picture, Abby, or are you just playing?
Just looking at my phone.
No, that's fine. I know I'm not that exciting, so. So again, if we look at kind of the next stage behind this, is what we were talking about with our chemistry is that electrophilic carbon and then somehow connected to a leaving group. Okay. Well, if we have an electrophilic carbon, what are we more than likely going to react this with? So I'll take some kind of nucleophile with electrons. Those electrons are going to come up and attack that electrophilic carbon. When they go through an attack, what are they going to do? Say that again, Josie? Okay. And so this becomes now kind of a mechanistic discussion. Should we kick out the leaving group, or should we break the pi bond? Why do you want to break the pi bond?
It makes more sense to break the pi bond than a sigma bond.
Why?
Something energy.
I mean, you're not wrong. What's the difference between a pi bond and a sigma bond? What orbitals are used to make a pi bond? P orbitals. What orbitals are used to make sigma bonds? Which one's higher in energy? That's why we break the pi bond. Okay. And Joseph, we are going to come back to your statement, because your statement is a lovely statement as well. And we'll use that to cheat our way through these. What's that? Yeah. So when we're going through and looking at these reactions, one of the things that we really have to watch out for is this tetrahedral intermediate. Okay? The tetrahedral intermediate is something that will get tested on. Okay? Either explicitly saying which of these is the tetrahedral intermediate, okay? Or it's going to ask something about the mechanism. And if you have a nucleophile and a leaving group that both have oxygen in them, you could go through and say, well, one of those oxygens is coming from the nucleophile, or one of them is coming from the leaving group. Where does it end up in your product? So understanding where your oxygens move through this reaction becomes an important cycle. Your electrons come back down. So this was that tetrahedral intermediate. We now have a dilemma. What do we kick out? Okay, we could kick out either the leaving group or the nucleophile. If it's this nucleophile, we go backwards. Nothing's particularly useful is done out of that. If we kick out the leaving group, what we're left with is then our new structure, a reformed pi bond. Come on, pen. Their nucleophile connected, and our leaving group with that pair of electrons. Okay. That looks a little bit like rainbow vomit. I apologize. Okay. And then you'll get all sorts of kind of questions going along the lines of, well, should this happen or should this not? Well, a lot of that's going to have to do with the stability of the things. What things are we talking about? There it is. Ultimately, what you're comparing is the nucleophile to the leaving group. What is the relative stability of those things? And you might go, well, you didn't show any negative charges, Mike, at least on those atoms. And I didn't show charges because it doesn't have to be negative. It just has to have electrons. Okay? To facilitate each of these steps, you may have a sequence of acid-base steps also integrating themselves within the mechanism. Okay? How do you know you're going to have those acid-base steps? Well, if you see an acid, you're probably doing some acid-base steps. You should take those into consideration as you navigate through your mechanism. Okay? If you don't see an acid, then it becomes a little bit more straightforward. Your nucleophile was probably negative and it's a direct attack. Okay? And that should follow more this standard pattern. If we break down the mechanistic steps, we've got our nucleophile addition. Okay? Again, this is supposed to be review, followed by our nucleophile elimination, and that's the new part. Whatever. Okay? That nucleophile elimination part becomes new, but in my experience, you've done the hard part with the nucleophile addition. Figuring out that last step of the elimination is really just being able to evaluate your difference between your nucleophile and your leaving group, which we'd already gone back through. Like Urban had already suggested that we talk about that. We talked about ranking their reactivities based off of leaving group ability. And I said, that's not fair. We can't do that. We're ultimately going to fall back on using that information to dictate whether the reaction happens or not anyway. Okay? So if you can follow this pattern now with all of your reactions, you've got a pretty good jump on this next exam. Kind of make sense? Okay. To me, what I would argue what we've done in the last now hour is all of the next unit. It's done. It's covered. Okay. There are for sure some nuances and exceptions within those, looking at specific reagents to see what's happening. But ultimately, you're taking the exact same reagents that you used in the last one for your nucleophile addition, and you just crank them all through again. Okay. Everybody's favorite reaction in the last one, remember the aldol? Yay, aldol. Okay. Gets like 4 other named reactions associated with it. Because what did somebody do? They went through and ran the aldol reaction again, except not with an aldehyde, but an acid derivative. Same chemistry, and they went, name. Nothing's changed about it, but they get to attach their name to it. They're like, oh, but there's a different acid derivative I could have done it with. Name. Fuck you. Okay? So you will see lots of names pop up through this. Okay? There's some subtleties within those reactions that helps to explain why someone should attach their name to it. I don't want to completely denigrate them, but your focus shouldn't be on the naming. It should be focusing on what's the chemistry associated with it. Okay? You still have alpha hydrogens next to that carbonyl, so you still have the potential to play with those. Okay? Kind of, sort of? Okay, I think I've taken over enough. What's the next thing you want to look at?
We have like 5 minutes left, so.
That clock says I got closer to 10.
Yeah, well, mine will watch this, but.
Oh, well.
How's your day?
Okay. OChem makes it better. What makes it crappy I shouldn't record, so I should just leave that one alone. And I should probably stop talking about it publicly because it's not a good look. There's no questions.
I could ask another open exam, that's gonna take more than 5 minutes.
We have the ability to do it now. What are we trying to make?
The anhydride.
We're trying to make the anhydride. What are we trying to make it from?
Amide and alcohol.
An amide and an alcohol. We actually answered this one in the last 60 minutes. Whoa, Irvin's already shaking his head. Okay, so there we go. I'm locked in. What do I do? Okay, the anhydride is above. I can't go up. I have to only follow particular pathways.
So we have to carboxylic acid
First thing I want to do is get a carboxylic acid. Okay, so how do I convert the amide to a carboxylic acid? Oh, I add hydroxide. It's like the previous question, just gave me the answer. Is that cheating? Should I not have done that? Okay. Hydroxide, officially we need a little bit of H plus on that too. Okay, step 1 and then step 2 maybe, which gets us our carboxylic acid. I need to go up. And I can't go up to the anhydride. I have to go up beyond the anhydride to drop down into it. So what was beyond the anhydride? The acid halide. How do I get to the acid halide? We'll use the SOCl2 because I drew chlorine. Usually, for whatever reason, it seems to me that most people write the acid chlorides than over the acid bromides. So SOCl2 is probably a more powerful one to memorize. Okay, that sets you up to this point. Okay, if we go through and look at our product in orange, there it is, right? There's that part. So what do I need on the other side? I need this piece. Where does that piece have to come from? It has to come from the alcohol. 1, 2, 3 carbons. 1, 2, 3 carbons. Cool. So what do I have to do to, we're going to call it the blue carbon. What does that have to become? Okay, let's convert it to an aldehyde. We could do that using PCC. Cool. Throw that up there. And then we tried to react these two, right? And then boom, we've got our product. What's the reactivity of our orange structure? Electrophile, yep, cool. That was the new one. You didn't know that one, so I'm being nice. Okay, what's the reactivity of the aldehyde? Okay, so we're getting a couple different answers. Like, well, you said the orange one was an electrophile, so the red one must be a nucleophile, so I'm going to say nucleophile. Okay, I understand where you're going with that, but is the red one a nucleophile? No, it's an. Okay. If we combined those two, would we get our final product? There needs to be another oxygen. And if we know the orange one is the electrophile and the chloride is going to leave, what must the red one supply? Do better than electrons. It must also supply the oxygen and the carbonyl. Do I want to convert it to an aldehyde?
So you do the bromate or the carboxylic acid.
Turn it all the way down to a chromic acid. Okay? If I use chromic acid, that fully oxidizes all the way to the carboxylic acid. Now what happens? The orange one is absolutely still an electrophile, but what does the red one produce? A nucleophile with that oxygen, and that oxygen happens to be exactly what we need to be able to do our attack. So we can do the nucleophile attack. Kicking out the leaving group right away wouldn't happen, but what we would do is break the pi bond. Okay? So that would all be one step. We can show our one step in green arrows, and then we're like, but I really don't want to draw the tetrahedral intermediate. I know it exists. So those electrons are going to come back down and kick out the leaving group. Okay? Which is what I said I was going to come back to with Josie, and then I forgot. Sorry, Josie. Okay? So this way we're showing all of those arrows, and some of you might be screaming, but you told me I'm not allowed to show all of those arrows happening in one step if they're not happening all in one step. You're right. I told you that when you were learning. What are you now? You are learned. Since you are learned, you can cheat as long as I'm not asking explicitly for a mechanism. What am I asking for here? I just want to know the reagents. What chemicals did you use to do this? That's it. Okay? So officially, wrapping it up in those last seconds, the official answer here I don't know why I wrote a 2 there. Didn't need a 2. That's all I need to see. Why do you have all that white space? So that you can set it up and you can prove to yourself that those reagents work, and that sets it up to be functional. That's the whole purpose behind all of that white space. I don't expect you to just divine that information to be able to vomit it onto the test. Okay? And in fact, I prefer you don't. When I see that, that usually irritates me. Now you know. Okay? I can't take off any points for it because it's all there. And you just did all that work in your head. That's great. That's awesome. But if you were wrong, I have to take all of the points away. And if you had shown any form of work behind that, I could at least try and track your thought process and your logic, and I can give you points for that. Make sense? See? Look at that.